And so the next speaker is going to be Seth Asante, who is a postdoctoral fellow at Jena University. And Seth is going to talk about effective spin-foam models.
Okay, thank you, Maite. Um, First of all, I must say I'm very happy to be here. It's nice to see all the friends from I made from back then, and interact with them, and also meet new people. So I'm very excited to be here. And also I want to thank the organizers of this conference for giving me this opportunity to talk about my work. And the task I was given is to talk about effective spin forms and give an overview of this topic. And it's a fairly recent um, topic in the spin form community, so I'll do my best to cover most of it. So I'll not go into very specific details of the model, but I'll give you a general idea what this model is. Also, I would like to thank my collaborators or people I work with mostly for all the wonderful discussions and things I have with them. Okay, but before I go into the effective spin form models, I just want to take this opportunity also to make an advertisement. So Pietro talked about this at the end of his talk on Monday. So there's a conference or a workshop, let's say, about quantum gravity on computer, just using dealing with computations related to quantum gravity, computing the complex amplitudes and stuff. So the workshop is going to be this year, September 9th to 13th. So just watch out for this. Okay. So let's begin. So I want to tell you why we consider effective spin-form models and what they are. But before this, we can think of this as like a motivation to why we consider effective spin-form models. And here I generalize it, just a slightly broad overview of what my interests are. So the main motivation is to understand what gravitational path integrals are. And here I mostly focus on discrete path integrals because this is like the language I'm coming from, spin form models and stuff. And if you have these gravitational path integrals, of course, what lessons can we learn from them? That's the main motivation of this work. And I mean, I put a bunch of words beneath this question, and you can think of them as like sub-questions. You can ask if you have a path integral theory or a formulation, and you can try and understand some of these questions. Like, for example, what's the nature of quantum geometry, which I would say is pretty much well understood in loop quantum gravity and stuff. Also, what's the nature of fluctuations at the Planck scale? What's the semi-classical limit of space-time? If you have a quantum space-time, whatever that is. So, a bunch of questions and, questions about cosmology, black holes, which I think is also motivation for some of the talks we've had in the parallel sessions and also in the plenary talks. For me, one of the most crucial questions is about renormalization or continuum limit, especially for these discrete models. And the reason is because, in these discrete models, your discretization is just like a regulator. And so you need to somehow get rid of this regulator at the end in order to make predictions or, do physics with it. And so so this is, the general motivation behind this. And you might say that, yeah, there are spin form models also one of the motivations, like how to make this, use the ideas from spin form models to tackle some of these questions. So that's all the motivations. And now let me tell you what the effective spin form models I'm going to talk about, what they are. So they are defined as some discrete geometric path integrals for quantum gravity. And the idea is to, let's look at the quantum geometry, which we've learned from loop quantum gravity, and let's keep the main dynamical principles or the key ideas in these theories. And let's ask, what can we get out of these key ideas? And the name effective in this effective spin-form models, I list here 2 reasons why we call them effective. So the first point is that, they are simpler models compared to general spin-form models. And I mean, there's a reason why they are simple, because we consider very simple amplitudes. But it's a way to, I see this as complementing the spin-form models, trying to extract the relevant dynamics from these models. So in this sense, they are effective descriptions of spin forms. And the other reason why they are effective is because they, in some sense, they give you a general family of models to play with. So here, I'm a little bit jumping ahead here, but we'll talk about some constraints here. So in this model, you can implement the constraints as you want. And in this sense, you describe like a general family of models in this sense. And so in this sense, they are also very effective. And also, like, since these effective spin-form models were constructed, we have gained some insights into general discrete path integral formulations. And here we will see that, we get some easy construction for Lorentzian and Euclidean models. And also you can study, semi-classical geometries. You can also do cosmology stuff just from these models. And one of at the end, I will touch on this. Like I mentioned before, one of the important results is the continuum limit, how to get the continuum limit of these discrete models. Okay, so with this, I'm going to talk about these 4, or let's say I split my talk into these 4 parts. I'll talk about the construction of these effective spin models. I'll give you the general idea behind this, and we go on how these models have been tested numerically, and give you some applications, and also talk about the continuum limits at the end. So let's see how we do. Okay, so this is the first slide about constructing these models. And here I list the references you can always look at if you want to understand or have a feel of what these effective spin-form models are. Okay, so the general idea, I mean, in this audience, I don't need to convince you so much what the key features of loop quantum gravity is or are. So here we start with the main, one of the key features, which is that your fundamental variables describing quantum geometry are in some sense described by area variables. What I mean here is, you associate your degrees of freedom to surfaces. Also in yesterday's talk, Mark, he mentioned, your charges are on the corners. So if you're in 4 dimensions, these are 2-dimensional surfaces. And so for us, the main motivation, or you can think of it, the idea here is that these area variables are, it goes back to these connection formulations, which Abai and many people have worked on. That's where these are coming from. But the idea here is that these area variables somehow describe you some enlarged space of geometries if you compare them to metric geometries. And so it's a good avenue to explore geometry or quantum geometry. There are also some other support for using these area variables from other approaches, like black hole entropy. We saw in the previous talk how the root Takanayagi formula is related to the area of some surface. And also entanglement, and so on and so forth. So there is good support for thinking about area variables as your fundamental degrees of freedom. And another key ingredient in, or like a key result from loop quantum gravity is that the area operators are discrete. Also, I don't need to convince you, we've heard many talks about how this discreteness come about. And here, I just state them here. But I can give you an intuition for this. So if you have time-like surfaces, you can think of this as they are conjugate to some angles, Euclidean angles, which are compact, so they are usually U1 compact. And then, so if you, in the quantum theory, this will be discrete. This will be discrete, right? And if you are space-like, it's a little bit more tricky. But if you use a Ashtika-Barbero connection, you can, and you take the holonomy of this connection, you can compactify them, and also it gives you some discrete spectrum. So this is where the discrete spectra are coming from. Okay, so with this, yeah, so given these dynamical principles, the question is that how do we construct a simple model keeping these key principles like the area, variables, and the discrete spectra? And here I go right into it. I give you the simplest action we consider, and it's called the area regime action. I think maybe for the students, you probably encountered this action in Bianca's talk. And if you don't know it, you can think of the area regime action as a discretization of Einstein-Hilbert action. We know this is the square root of G times the Ricci scalar term. And here, if you discretize it, you get Regge calculus, but usually it's expressed in terms of metric or length variables. But here we express it in terms of area variables. So the variables you see here, the A of t is the area of some triangles. And before this, I must say that these are defined on some triangulated surface. So you have some discrete surface which are made of triangles. If you are in 2D and you can keep going higher level in higher dimensions, there will be simplices. So, so the definition of the action here is that, and these epsilons, epsilon t, are some angle variables. They are called deficit angles. And they measure curvature of your, let's say, discrete spacetime. And so the definition of this action here, you can think of it as, you have curvature concentrated on your codimension 2 surfaces in 4 dimensions. Those are triangles. And then it's distributed over your discrete spacetime, and you weight them by the area of each triangle. So that's so it gives you some discrete GR action. And the relevance of this action has already been discussed. I think it was first initially mentioned by Carlo in '93. And this was, the idea was that, Bolzano-Regge model and Tureviro model was well understood, but these were in 3 dimensions. If you want to, carry this to 4 dimensions, Carlo realized that then the variables that might be relevant are these area degrees of freedom. And so the area regime action might be important. Yes, like you color your representation theory data with areas instead of length. There are also many other motivations. So here I cite Barrett, who they've worked on asymptotic limit of spin-form models, where also these area actions, area regime action appear if you consider just one simplex that, in some semi-classical limit, then you find that these area regime actions appear. Okay, so we consider this action, and okay, if you consider the classical dynamics, so the classical dynamics of this action will be varying with respect to some area variables. What you get is that you just get that the deficit angles, which are here, is equal to 0. And you can get this by using some Schliffli identity, which is well understood. But the caveat here is that this dynamical equations doesn't reproduce for you the discrete GR dynamics which you would expect. So because, if you are, so you can interpret this as, or before this has been interpreted as giving you only flat configurations, but, because you are dealing with area variables only, it's a bit tricky. It's not just vanishing of curvature, but also some shape matching things going on. So, but the long and short is that still you don't reproduce discrete GR dynamics as you expect from the metric variables. But aside that, we can write down a preliminary state sum model, which is take this action and exponentiate it and put some measure and sum over all the discrete areas. And this defines for you some state sum. But we know from this classical dynamics is that if you write these state sum models, it might not reproduce for you your GR dynamics. And so the idea is that you have to impose some constraints which will take you back to the GR dynamics, at least in the semi-classical limit. And these constraints have already been discussed by Bianca and Simone in some paper, but there they actually studied a different version, which is area, angle, Regge calculus, but the constraints are also defined there. But for the purpose of this talk, I give you a different formulation of these constraints. And the idea is that, okay, you have a triangulated space, so you have a bunch of triangles or simplices, and for each area you can represent, you can write down using Heron's formula, so it's a very old, ancient formula, describing the area in terms of the edge length of a triangle. So this is the formula given here. And if you write this for all the triangles in your discrete spacetime, this gives you the set of constraints that you want, right? And you can compare this to the simplicity constraints that appear in spinform models. So how do we solve these polynomial equations? Because now if you write this, if you take this as the area squared, then this defines for you some polynomial equations. So, if I have a triangulated spacetime and I write all these equations, I get a set of polynomial equations. And how do I solve them? And here, so recently, together with Taylor, he's a mathematician at Western, we used some techniques from homotopy continuation. I mentioned this here because I think this is a very powerful method. And if you are working with anything which has to do with polynomial equations, I think these methods are very useful. So you can always look here for some tools. So the homotopy continuations are tools from numerical algebraic geometry. And what they do for you, they don't just solve you nonlinear polynomial systems, but they can also give you some algebraic and some geometric properties of your system. And this is exactly what we do here. So just to give you an intuition, like if you consider a four simplex, which is usually represented by this diagram here in 2D, a four simplex has 10 areas. So if I write down these constraints, I get 10 equations for 10 areas, right? And then I can use these tools from homotopy continuation to solve these polynomial equations. And what we found was that for these 10 areas, there are up to 64 length solutions, configurations for a fixed set of areas, which means that there are up to 64 metric configurations that you can associate to a particular area configurations. But I say up to because this is in the complex space. So you complexify this length. But if you want to somehow reduce to only real length, then this can reduce, the number 64 can be reduced. So not just that, so I mentioned some algebraic and geometric properties. It gives you a powerful method to study what we call here the Galois group for these polynomial systems that you consider. And here we studied that the Galois group associated to this polynomial system for just one simplex is given by this Z2. Actually, the 2 should be down, but it's the same. So Z2 with product, some symmetric group. And what this gives you is that if you know the Galois group, it can tell you whether these polynomial equations are solvable or not solvable in terms of like radicals, let's say. So, having this as the Galois group, we already know that these system of equations are not solvable. So if you sat down to try and solve them by hand, you could not do it. So that's also why these homotopic continuations are very powerful. Okay, so I mean, if you're wondering about these diagrams, this is like the count of the 64 solutions. It's actually encoded in this picture. So each color of the length represents some different edge. So for example, in this, there is one different length and then 9 equal lengths. But there are like 10 permutations of this. There are 15 permutations of this. And if you do the count, you get 64. So that's why I put this here. Okay, so, but this is for just one simplex I showed you. But if I consider like a big triangulation and I write down this set of polynomial equations, what's the solution I get? Usually you find that there are no solutions or very few solutions depending on the set of area parameters you have. And I mean, also together with Bianca and Howard, we show that if you now say even your area variables are discrete, they have discrete spectrum, these polynomial equations gives you some Diophantine equations, and they almost assure you that there will be no solutions, or very few solutions, right? But there's also another way you can think about these constraints that I'm describing here. You can think about that, if I have a triangulated spacetime, I have two simplices. Two simplices are usually glued along a tetrahedron, and the areas of this tetrahedron match. But if I want to match the length geometries, then I need 2 more degrees of freedom, and these can be encoded in some dihedral angles. So there are 2 extra degrees of freedom you have to match in order to match these geometries. Okay. So I mean, the situation I've described to you up until now, we are in sort of like a state of dilemma, let's say. And I copied this from Hal, as he's from previous talk. I like the way he put it. So this is from some Greek mythology. We are in between 2 evils. Where should we go? We are like, using the area variables, we have too many degrees of freedom to capture. And so if you impose the dynamics, you don't get GR. But also, if you impose the constraints, we saw that you almost get no solution. So what do? Which one should we go? So you are either Scylla or Charybdis, or I mean, this picture, do you hit the rock or fall down, go down? But so there's a way out, and the way out here is to so you go back to the constraints, which I represented in terms of these angles, and you can localize these constraints by introducing some angle parameters here for every tetrahedron, and enforce that these angles, the 3D angles I told you about, that they are equal for every tetrahedron, and this localize for you these constraints. And these constraints have been studied in, like say, in Karpowicz-Mirchin phase space, where they studied it's the phase space of deformations of a tetrahedron, and you can compute the Poisson bracket for these constraints, and you find that it's second class, so it doesn't vanish, or if you compute the Poisson bracket. And here I want to stress that these constraints, the Poisson bracket, is proportional to this gamma parameter, which is the Barberi-Imezi parameter, which also appears in loop quantum gravity, as we know. So you have these second-class constraints. So the leeway is that you cannot impose these constraints too strongly, because that goes against quantum mechanics as we know it. So you have to somehow impose the constraints weakly, but as strongly as allowed by these uncertainty relations. And this is actually you can think of it as the same philosophy also used by the EPRL spin forms, right? So the idea here is you can use this some coherent states also from the EPRL models. You use this coherent state and you know the current state for these angle variables, and somehow you can integrate out these angle variables. And if you integrate out these angle variables, it gives you some coupling, okay, between, yeah, it gives you some coupling between the simplices. Right. So, at this stage, I have defined for you all the ingredients of the effective spin forms. So we have the area reaction and some gluing constraints, which measure, or let's say, yeah, which defines for you these constraints. So those are these Gaussians that I defined previously. So these are Gaussians, and these are somehow oscillating. And okay, so the idea here, I just summarize, what I mentioned for you here. So the features of these models are they are very effective. They, in the sense that they keep the dynamics of LQG, and they are very computationally efficient. And also, I did not mention this, but they are related to some higher gauge theory. And like this area action, you can define both Lorentz and Euclidean, so they are very simple. And they are also they have been applied. They are cosmology application, so on and so forth. Okay, and before I go into some details, I just want to mention one important features which we encountered, which is that if in the Lorentzian theory, you have some weird configurations, which we usually call them regular or irregular configurations. And the idea is that, if you have a triangulated space, so here I represent in 2D, these triangles are each are considered flat. So you can draw some light cones for these triangles. And if you draw a light cone, and if I have like a triangulated space and I count the number of light cones at, let's say, every hinge, sometimes I don't just get 2 light cones. Like, if you have 2 light cones, that's a regular configurations, but you can have more than 1 or 2. So these we call the irregular configurations, and these are somehow very generic. There are also higher dimensional versions. But here the idea is that if you have these irregular configurations, the area rejection I told you about, you find that they are complex. Okay. So, and another thing I wanted to mention is that, there are many techniques for dealing with complex amplitudes. So here, I just stated them here just so that people are aware of them. But the recent techniques is these acceleration operators, which has been used in EPR and also in effective spin-form models. And it's to help accelerate some sums of convergence. So if you have a slowly convergent series, if you use these acceleration operators, it can increase how these sums converge. Right. So now I go to the testing of these models. I don't have much time, so I'll be very quick here. But to tell you about, we have oscillating amplitude and we have some Gaussian. So this is so this example here is an actual example for a delta 3 simplex, if you know it. But so usually you have oscillations and then you have some Gaussians. And the idea is that, in some large limit, or if the areas are large, the oscillations will be very fast. And if you have a Gaussian, then, the oscillations might die out. So if you want to get a very good semi-classical limit, you have to give like a relation between how the relation that the number of oscillations under the Gaussian is of order 1 is given by, let's say, this condition here. It relates for you this gamma parameter and areas, and also the curvature, which are some parameters in your model. And also, the similar idea also comes from these complex critical points, which you can also mention. Okay, so the idea is that what effects can we get from the discrete area spectrum that I told you about, and these weakly imposed constraints. So we've tested this, and the long story short is that we recover. So we do this for very explicit computations. These are non-perturbative tests we've done for several triangulations, and we recover discrete gravity dynamics for in certain range of parameters, which is very nice. And here I show for you some plots which compute expectation values of some area operators. And the surprise was that, you can do this for a very, you can do this plot for several values of gamma. So here I show you some continuous gamma plots. And yeah, so in this example, you see that, in this range of gamma, my expectation value for some bulk area operators matches the classical value very well. So this was a very nice surprise. And beyond the saddle point approximations, there are also some nice features or some interesting features you can see from these plots, and this can all be explained. And the idea here is that if you have a discrete area spectrum, which is in this picture, there are some pseudo saddle points here, which you wouldn't see if you have a continuous area spectrum, but in the discrete spectrum you see it, and this is the reason why there are these bumps here. Anyway, so I go quickly through the cosmology application just to mention that it's been explored for this no boundary proposal and the zeta cosmology spacetimes, which we've heard also throughout this conference, and also for the spatially flat cosmology, which is, and this afternoon there's a talk by Alex on the spatial flat cosmology keys. And these can be compared with also the spin-form cosmology talks we had on Monday. Okay, so here in effective spin-forms, this also has been done. And so there, the thing you have to worry about is, you have these slowly convergent sums that you have to deal with. And the acceleration operators I told you about are very useful here. And also another interesting thing is that you have to sum over both regular and irregular configurations, the configurations with weird light-cone structures. You have to sum over all of them. And it has been done by Jose and Bianca. And for example, in this model, in this de Sitter model where you go from an initial scale factor to a final scale factor, one can show that these techniques work very well. But maybe in this no boundary proposal, it's not matching very well, and this can be due to some discretization effect and so on. Anyway, so the last thing I wanted to touch on is this continuum limit I mentioned in the beginning. So, and there, if you take your effective spin-form partition function, you can rewrite it, and then the action that comes out is something of this form. And here, so these are first attempts to studying the continuum limits of these models. And here, it's done at the linearized level. So you do this on some hypercubic lattice, and and then you do a linearized version. So you linearized your action around this. So the main thing you want to compute are some Hessians. And the results that I wanted to briefly mention is that even without this constraint term, if you only focus on the area regi action, one can show that in the area regi action, you get linearized GR, which was very surprising, plus some Weyl square terms. Okay, and those Weyl square terms, the important thing is that they are subleading compared to the linearized act. Okay, and also, if you include these terms, it doesn't change this picture. And there are also some very important related works, also by Johanna, starting from the spin-form Plebanski actions and trying to derive effective actions from there. Okay, so here it was just to give you the mechanism behind this. These continuum limit works. The idea, like I mentioned, is to compute the Hessian of these actions around some background. And this, there are some techniques from way back by Ruth Williams and Martin Roszek. And and also it has been extended also together with Hal. You can also do this for area regi. And the difficulty here is to organize all your variables that go in here into some nice form. And I would say maybe the important results that came out is that you can organize your variables into some area metric variables. And these area metric variables split into some trace path and some trace-free paths. And the trace paths give you the length configurations. And these chi fields are non-metric degrees of freedom. And if you then find the the effective action for these non-metric degrees of freedom, what it gives you is basically this form. And this part is the linearized Reggie part, and this part is the vi-square term that I told you about. Okay, so this, in summary, this was just a very quick overview of what effective spin forms has been used for or has been done lately. And I go back to the question I asked in the beginning, which is that what can we learn from this discrete gravitational path integrals? And using effective spin forms, we saw that you can do some semi-classical approximations, which I showed you some tests, and also there are some cosmology applications, and also first baby steps of finding continuum limits of these theories. There are many other questions to explore, just like in this, but at the end, we want to look for some signatures, some very concrete signatures starting from these area variables that we all have. And the works by Johanna is very important works in this direction. So this is the end. Thank you.
Thanks, Seth, for the very nice review. So we have 3 minutes for questions. So let's see. Yeah.
So in those early universe cosmology applications, are your results? Do you recover the loop quantum cosmology models, or you obtain different results?
Okay, so I don't think we are at the level to compare those yet. So what is being studied here are just trying to compute you write down the partition function or the path integral for these cosmology models. So you have, some, let's see, for these models, you discretize you have let's say a discrete triangulation for these de Sitter space models. And then once you write the path integral for this, you can compute some expectation values of some operators, and then you compare it to the classical value, what you would get. And this was the comparison we've done. So we are not at the level of, let's say, if determine if there's some bounds or anything. No, we've not done that yet.
And what about the the path integral models obtained from loop quantum cosmology? Can you compare your models with those?
I would say yes, but it's not been done yet. If we can compare, probably yes. Yeah, but yeah, I have to check these things.
We have time for one more question now. Okay, if there is no more question, let's take Seth again.